Hey guys, today we're going to have a look at probability, whether it's the probability of rolling a certain number on a die, or picking a certain card from a deck of 52, or finding a four-leaf clover in a field of clovers. Let's start with the basics of a probability scale. Now we can show chance as being a way of defining how likely something is going to happen, but chance is usually a word like impossible or very likely, whereas probability is a more exact way of defining the likelihood of an event because we can use numbers to express probabilities as fractions or decimal values, between 0 being an impossible event and 1 being absolute certainty. Now, notice I didn't mention percentages here. You can use percentages to describe probability, but I don't like getting into that because when someone says the probability that something will happen is 50, that's way more than it's allowed to be. The most a probability can be is 1, or in percentages, 100%. So that person who said the probability is 50 means 50%, which I would prefer that you say is 1/2 or 0.5. So let's try to avoid that problem with the percentages, please. So on our probability scale, let's show the lowest possible probability and the highest possible probability as 0 being impossible and 1 being absolutely certain. Now, as you can see, I've split my probability scale into 10 different sections. So each of these sections represents 1/10. This would be 1/10, this would be 2/10. So I can write that as 0.2 or 2/10, or simplifying that fraction, 1/5. 3/10, 4/10, 5/10, that's halfway, or 0.5. 6/10, 7/10, 8/10, or 0.8. 8/10 is also the same as 4/5, 9/10, and then we get to a whole. So we've split this probability scale down into tenths, but you could split a probability scale into infinite numbers of sections. So don't think that these are the only probabilities that you could be given. Now, when we talk about something being impossible, it's very difficult to think of something that is completely impossible. For example, what's the chance that I wake up tomorrow and my dog Coco is turned into a unicorn? Pretty unlikely, but I don't like to say impossible because maybe there is such thing as magic. So I'm going to put that down here on my probability scale. And what about certainty? I'm pretty good at setting my alarm, and whenever I hear my alarm ring in the morning, I generally get up. So I would say that I'm pretty sure that I'm going to wake up tomorrow when my alarm rings, but I'm not positive. So I'm putting that pretty close to the end of the line, not quite certain, but pretty sure. Okay, and you can put all sorts of probabilities on this probability scale, like the probability that it'll be sunny tomorrow. Now, we're in the beginning of summer, we're in Mallorca. It's pretty likely that it's going to be sunny, although we have had some cloudy days lately. Now, simple theoretical probability uses the fact that an event has a set number of possible outcomes, which are equally likely and mutually exclusive. This is important wording that you're going to need to get down, but let's explain this. Now, for example, rolling a die. That's singular for dice. That is the correct spelling. When you roll a die, there are a set number of possible outcomes. We could get a 1, a 2, a 3, a 4, a 5, or a 6. Those are the possible outcomes. We can't get a 23, for example, unless it's a special die. So there are 6 possible outcomes. So long as it's a fair die, so that means that when you roll it, it's equally likely that it will land on a 1 or would land on a 6, then we would call that a non-biased die. So a fair die has 6 numbers and they are all equally likely to come up. So the probability that I roll a 1 is the same as the probability that I roll a 3, for example. So that's equally likely. And mutually exclusive, this is the difficult one. To explain what mutually exclusive means is to think that it's not possible for it to be one outcome at the same time as being another outcome. For example, if I roll my die, it can't be both a 3 and a 5 at the same time. It's either a 3 or it's a 5. So it would have to be one or the other. That's mutually exclusive. So given those definitions, simple theoretical probability is worked out like this. The probability that some event happens, I'm going to call that event A. The probability that event A happens is equal to the number of ways that A could happen out of the total number of possible things that could happen. Notice my notation here. I'm talking about the probability that event A happens. So I do a capital P and then in brackets I put what the event is that I'm checking the probability for. So for example, the probability of rolling a 4 on a die would be 1 out of 6 as well, because there's one number on the die that is a 4, or there's one side on the die that's a 4, out of 6 sides altogether. So 1/6 of the die. The probability of rolling a 2, similarly, is going to be 1 out of 6, because only one side of the die is a 2, and there are 6 sides to the die. The probability of rolling a 7 on a fair die, however, is 0 out of 6, or just 0, because looking at a normal die, there are no 7s on a die. So there are 0 possible ways to get a 7 out of 6 possible outcomes. The OR rule. Now this only works if your outcomes are mutually exclusive. So this is when we're talking about the probability that one event happens or another event happens. The probability that A happens or B happens is the probability that A happens plus the probability that B happens. Only if these cases are mutually exclusive. So raining and snowing are not mutually exclusive because it could happen both at the same time. It could be raining and snowing at the same time. However, rolling a die, for example, rolling a number higher than 2, that means it's a probability that it's 3, 4, 5, or 6. It couldn't be all of those numbers at the same time. I've just rolled a die and I see a number on it. What's the probability that it's a 3, a 4, a 5, or a 6? Well, for that, I would add those probabilities together. So I would do the probability that it's a 3, plus the probability that it's a 4, plus the probability that it's a 5, plus the probability that it's a 6. In all cases, the probabilities were equally likely and they were all 1/6. So that'd be 1/6 plus 1/6 plus 1/6 plus 1/6, which is 4/6, or that simplifies to 2/3. Let's have another look at an example. So rolling a prime number. Prime numbers on a die, 1's not prime. That's 2, 3, 4 is not prime, 5, 6 is not prime. So 2 or 3 or 5, those are mutually exclusive outcomes because it's not possible that I've rolled a die and it's both a 2 or a 3 at the same time. So I'm going to add those probabilities together, the probability of a 2 plus the probability of a 3 plus the probability of a 5. Again, we already worked out these probabilities. They were all 1/6. So that's 1/6 plus 1/6 plus 1/6, which is 3/6, or that simplifies to 1/2. Let's take a step away from those die examples and think about something else in normal everyday life. What's the probability that you were born on a weekend? Well, the weekend consists of the 2 days, Saturday or Sunday. So the probability that you were born on a weekend would be equal to the probability that you were born on a Saturday plus the probability that you were born on a Sunday. Now, what's the probability that you were born on a Saturday? There are 7 days in a week, and Saturday is one of those days. So the probability you're born on a Saturday is 1/7. Same thing with Sunday. There are 7 days in a week, and one of those days is Sunday. So the probability that you were born on a Saturday or a Sunday would be equal to 1/7 plus 1/7, which is 2/7. The probability you're born on a weekend is 2/7. Another thing that's important to remember about probabilities is that the total probability is 1. That's a certainty. So if you think about all of the possible outcomes and you work out the probability that any of those outcomes happen, it should add up to a probability of 1. So the probability that something happens or doesn't happen, that's all of the possible outcomes. That should add together to be 1. So our notation for this, if we're talking about event A happening, we could say the probability that event A happens, or, and then this A with a little line up here means not A. So the probability that an A happens or not A happens is 1. And of course, we know the OR rule. The probability that something happens or doesn't happen, They're mutually exclusive events, so I can add them. Whenever it's or, we add. So probability A plus probability not A needs to add to 1. Now let me put this into context for you. The probability that it rains tomorrow or that there is no rain tomorrow. These are all of the possible outcomes. Either it rains or it does not rain. So this should add up to a total of 1. Let me put that into the correct notation for you. Probability of R, or the R with the little line at the top, not R, is equal to 1. And because they're mutually exclusive events, probability of R plus the probability of not R equals 1. So this is our correct notation. Now, what if we're told that the probability that it rains tomorrow is 0.35? Well, that would mean we could work out the probability that it doesn't rain easily, because I know that the probability that it rains plus the probability that it doesn't rain should add to 1. So let's work that out. The probability that it rains, 0.35, plus the probability that it doesn't rain is equal to 1. So algebraically, if I want to know how much the probability is that it doesn't rain, I'll need to move this 0.35 to the other side. On this side it's adding, on the other side I'll subtract it. So the probability that it doesn't rain will be 1 minus 0.35, which is 0.65. Now, theoretical probability is what we generally start with, but sometimes it doesn't make sense to use theoretical probability. For example, there are 26 letters in the alphabet. What's the probability that the next person you meet has a name beginning with A? Theoretically speaking, so not really thinking about your past experience, the probability that the next person that you meet has a name beginning with A is 1 out of 26, because their name could begin with any of those 26 letters, but you're choosing one of them. Experimentally, you could actually think about past experience or conduct an experiment. For example, I have 300 contacts programmed into my phone, and 20 of them have names beginning with A. A is quite a common letter for a name to start with, so I can work out the probability of a name beginning with A based on what I know. The probability that the next person I meet has a name beginning with A is likely to be the same proportion as the people I already know with a name starting with A. I know 20 people with a name starting A, and I know 300 people altogether. So the probability of someone having a name starting with A, based on my past experience, is 20 out of 300, or 1 out of 15, as that simplifies dividing both top and bottom by 20. Now, let's do another example. I rolled a biased die. That's not a fair die, a die that is showing up some values more often than others. And I rolled it through 30 times and it landed on 1 3 times. That doesn't seem like very much. Theoretically, I would think that the probability of rolling a 1 would be 1 out of 6, because there's one side of the die with a 1 out of 6 sides of the die, so 6 total outcomes. Experimentally, I've just worked out that in my 30 rolls, I got 3 1s. So the probability of rolling a 1 based on this experiment that we've just done is 3 over 30. Now that can simplify to 1/10. And you can see that 1/10 as a fraction is smaller than 1/6. If you need to work it into a decimal to see that, you can do that. But it's less likely that it lands on a 1 than I would have expected. Speaking of expectations, let's think about what we were expecting to happen. We could expect an event to happen all the time, which means that its probability is certain. It's a probability of 1. Or we could expect that it would never happen. It's impossible, probability of 0. Or generally, we expect something to happen a fraction of the time. This is why probability is given as a fraction. So our expectations is the expected number of successful outcomes, the expected number of times we expect something to happen, would be a fraction of the number of tries we take, the number of attempts. So our notation for this is the expected number of times event A happens, so E, and then in brackets, the event A, is equal to the probability that A happens, which will be a fraction, multiplied by the number of tries. So it's basically just a fraction of the number of tries. So let's go back to our biased die. Theoretically, we thought the probability of rolling a 1 was 1/6. So how many ones did I expect in 3 rolls? My expected number of ones would have been 1/6 of the 30 rolls, because the probability of rolling a 1 is 1/6. I expected a 1 1/6 at a time. 1/6 times 30 is 5 times. I had expected to see a 1 5 times in the 30 rolls, and I only saw it 3 times. Now keep in mind that luck is unpredictable. We never know exactly what's going to happen. So that must mean that anything's possible. Maybe Coco will turn into a unicorn. Let's do some practice. So go through these questions, hit pause, and work through your answers, and you see your answers at the end. Question 1. In a pack of 52 cards, there are 4 suits. That's clubs up here at the top, diamonds, hearts, and spades. Now, look, you've also got all of these number cards from ace, which is 1, up to 10. And then we've got face cards, which are jack, queen, and king, for all of the different suits. You've got 2 suits which are black and 2 suits which are red. So that should help you if you're not used to using these kinds of cards. Work out the probability of picking one card and getting these results. So the probability that you chose one of these cards and you got the 3 of hearts, or you got a spade, that's one of these ones, or you got a black card, or you got a face card. Question 2. There are 6 girls and 4 boys in a class. Work out the probability that the next one to have a birthday will be a boy. Note my probability notation here, P, boy birthday, and work out your probability as a fraction. Work out the probability that the next one to have a birthday will be a girl. So again, my notation, P, girl birthday, and work out your probability as a fraction. Question 3. A box of sweets contains 5 blue sweets, 3 red sweets, and 12 yellow sweets. If I randomly chose a sweet from the bag, work out the probability that I choose these colors. So I'm just choosing one sweet. What's the probability that it's blue? Remember to use this notation. What's the probability that it's yellow? What's the probability that it's purple? What about the probability that it's red? Or the probability that it's red or yellow? Now continuing with this, what if I randomly chose 12 sweets now from this bag? How many blue sweets would I expect to have chosen? Remember, there are 5 blue sweets, 3 red sweets, and 12 yellow sweets. How many blue sweets do we expect? Remember the notation, expectation, capital E, and then in brackets, the event, blue. Okay, I hope you've hit pause to work these through, because here come the answers. For question 1 about the cards, A was 1/52, B simplified to 1/4, C simplifies to a half, and D, you could have written 6/52, but I'm hoping you would have simplified that to 1/13. Question 2, the boys and girls. The boys have a probability of 4/10, or simplifies to 2/5, and the girls have a probability of 6/10, or 3/5. Question 3, our sweets. A is 5 out of 20. I'm hoping you're simplifying though. Both top and bottom divide by 5, so 1/4. B is 12/20. Both top and bottom divide by 4 though, so 3/5. C is 0 out of 20. There are no purple sweets. So that's a probability of 0. That's impossible. D is 3/20. And E is 15/20. Or dividing both top and bottom by 5, that simplifies to 3 over 4. And I would expect 3 blue sweets. Okay, have a look over those answers, correct yourself, see if you have any problems, and let me know.